All right, guys, let's get going into section 4.2. This isn't too long of a section. As I'm looking at it here, it looks like we have about 8 slides, and it's mostly on vocabulary. That said, I'm not sure I'm going to be able to get all of this done in one take right here, so we might have to break this up into 2 videos, but let's get working on it. Remember where we are, guys. In Chapter 4, we're taking all the skills that we picked up in Chapter 3 about how to find a derivative, and now working on applications of the derivative. So what we are working towards right now is using the derivative of a function to figure out what that function itself looks like in terms of its graph and in terms of its behavior, but also in terms of where this function takes on what we're going to call today are extreme values. And if you think about the word extreme in an English context, I think you know already where we're going. The extreme value of a function is going to be where this function takes on a value that's different and significantly set apart from the other ones around it. So we're going to try to break this up here. And first, in part 1 here, start talking about types of extreme values. And the first type of extreme value we're going to discuss here is what's called an absolute extreme or a global extreme. This absolute term is probably the more technically correct one, but I was always taught to talk with global right here. And they mean kind of the same thing. So let's get into the first part of our definition here, guys. F of A, and let me stop you right there and remind you that when we say f of A, we're talking about a y value here. F of A is the absolute maximum of your function if, and here's the important thing now, guys, this y value, f of A, is greater than or equal to some other y value, f of B, for all B in the domain of f. Okay, that's a lot going on right there. What we're essentially saying, guys, is that a y value would be the absolute maximum of your function if that y value is higher than, greater than, or equal to, there can be a tie there, all other y values on the graph. And the simplest example of a graph with an absolute minimum would be, an absolute maximum would be something like a downward opening parabola. And as I think you could probably guess, the vertex of that parabola right there is the absolute maximum of that function, or I should say that's where the absolute maximum occurs, because that one y value right there is higher than, or its y value is greater than, every other y value in the entire function. Okay, not real complicated to understand. There's another version of this definition right here as well, and it's pretty much exactly the same, it just flips things around. F of A, again a y value, is an absolute minimum of your function if that y value is less than or equal to every other y value here in the entire function. And so obviously that one would be best illustrated by maybe an upward opening parabola, where this y value right here at the vertex is our absolute minimum because it's lower than every other y value on the entire function. So absolute or global extremes, guys, I always like to think of that in terms of, I'd ask you this question, and a lot of people know it, the absolute highest point on Earth, everybody, is Mount Everest, I believe. And I don't know the elevation up there, but it's pretty high, 28,000 feet, something like that. If only we could Google this and figure it out. Anyway, the point there is that if you were standing at the top of Mount Everest, you would be at the absolute maximum, highest point on Earth. There is nowhere on Earth, anywhere around, that is higher above sea level than that one point right there. That might become more relevant when we start talking about the next thing. So, that was A, everybody. That's our definition of an absolute or a global extreme. But now for B, we're going to amend that a little bit and start talking about what's called a relative or a local extreme value. So let's break this one down and let's take a look at this definition here. F of A, again, this is a y value now, is called a relative maximum of your function if your y value, f of A, is is greater than or equal to, let's try that again, greater than or equal to f of B for all B, now this gets interesting, in some closed interval containing A. Okay, that's a mathematician's really, really wordy definition right here, but let me go ahead and draw you a picture of what's going on right here. A relative maximum would occur if you had, let me draw maybe like a fourth degree polynomial function that does something like this. You've seen a few of those here and there over the years. All right, guys. Now, we just got done talking on the previous slide about an absolute maximum. The absolute highest point right here, everybody, that is greater than or higher than every other point on the entire function. So that point there is the absolute max. That's Mount Everest. But this point, located right over here, is kind of important too. That point right there, guys, is what we call a relative maximum. Why? Well, what's important about that point is that its y value right there is greater than or equal to every other y value immediately around it, both to the left and to the right. That is the highest point. So if your absolute max up here was more like Mount Everest, this one right here, a relative max, might be something like Mount McKinley in Alaska. And if I'm not mistaken, Mount McKinley is the highest point in the U.S. So it's not the highest point on the entire globe, everybody, but you're still pretty darn high up right there, and you're higher than everywhere else immediately around you. What's important with a relative max, everybody, is that as you move to the left of your point, as you move left from that point, the function goes down. As you move right, it goes down as well. And when a point goes down in both directions, you are dealing with a maximum. Okay, let's move on to the second part of this here, although I don't think understanding this is going to be too tough for you if you got the first part. F of A, your y value, is a relative minimum of f of x if f of a is less than or equal to f of b for all b in some closed interval containing a. And actually, I'm going to switch colors on you guys here yet again, and I'm going to go to a lovely shade of green right here. So actually, for the relative minimum, let me underline that in green, because let's go back to the same graph that we had right here. What you'll find, and we'll get into this in just a moment, this graph that I drew, this downward opening fourth degree function, does not have an absolute minimum. There is no low point on this graph because with the arrows pointing down in either direction, this thing just continues to get lower and lower and lower with y values tending towards negative infinity. So this graph has no absolute minimum. But in terms of a relative minimum, is there one point that's lower than all the points around it in both directions? And the answer to that is yes. You've got that one happening at this point right over here. That is what a relative minimum looks like. And again, back to the red arrows I used a moment ago, part of the reason why this is a relative minimum is as you move right from that point, the function goes up, and as you move left, the function goes up as well. So when the curve goes up on both sides or in both directions, that's when we're dealing with a minimum. Okay, so those are our definitions. And now what we're going to do for the next, 1, 2, 3, 4, 5 graphs, I think, is we're just going to take a look at a couple of examples here and see if we can't kind of get the sense for what things look like. So all I called this section right here was classifying extrema, and this is a really informal way of walking through it, guys. I've used kind of the geometric method of just naming points with a single capital letter and not making them an ordered pair like, little a, comma, f of a, stuff like that. All right, so what's going on right here? I've pinpointed here or named 3 points along that curve here, which kind of looks like it's part of a parabola, but that doesn't matter. And notice, everybody, I did not put arrows at the end of this thing. I'm not saying this thing goes up forever the way that a true polynomial does. I'm just saying this function exists on a limited domain. Okay, well, even though I've put them in order here, A and B and C, I usually like to think about them in terms of the order that we presented them here. An absolute maximum, the highest point on the entire graph, yeah, we've got one of those right at point C, everybody. That one, nope, screwed it up already. Point C, that is our absolute maximum. There's no other point on this graph higher than C. Next one, absolute minimum. What is the absolute very lowest point on this graph? That's going to be point B. There's nothing lower than that point there, so B is our absolute minimum. And then what's going on at A? A is not the absolute max and it's not the absolute min, but being one of the endpoints right here, it is important. And what we can see is that in a small neighborhood directly around A, that point is higher than any of the points immediately around it. Let me clarify. Point A is higher than these points over here on the left, on the right, and there are no points over here on the left to compare either. So A, everybody, is our example of what we call a relative maximum, because it's higher than any of the points immediately around it. And that's it. That's A, B, and C. All right, so that's where we are with example A. Let's take a look at what's going on in B. And you'll notice in B, I drew a cosine wave. I didn't put any particular points right there. And that's because I think by actually knowing what the function is, I think we can probably answer this question, although it is inconsistent the way that I phrase this right here. Let's talk about absolute maximum. And the real question here is, everybody, does this cosine wave have an absolute maximum? One point that's kind of the Mount Everest, that's king of the hill, that's higher than every point around it. Now, a lot of people are tempted to say no, but I've got to take you back to the very definition right here and point this out. Our definition of an absolute maximum is a point right here where f of a is, that was supposed to be red, where f of a is greater than or equal to f of b. So we need a y value that is greater than or equal to every other y value in the range of the entire function. And the answer to that is, yeah, we do have it. The highest that cosine is ever going to get is 1. Now, we want to interpret this carefully, okay, because obviously there's a peak here, there's a peak here, there's a peak here, and with the arrows that I've drawn, that suggests that this thing is going to continue to go on forever and ever, amen. Now, we want to make sure that we say this correctly, okay, so I want you guys to listen very carefully. This function, b, only has one absolute maximum, and that absolute maximum is 1. But what we would be able to say is that this absolute maximum occurs an infinite number of times. But it would be incorrect to say the function has an infinite number of absolute maxima, because an absolute maximum, really any of the things we're talking about, these are y values. And it doesn't have an infinite number of y values that are the biggest. Only one of them can be the biggest. So your absolute maximum is 1. Going along with that, I think you guys know what's coming next. We have an absolute minimum here. The lowest our y value is ever going to get is -1. And again, that occurs an infinite number of times or at an infinite number of points. But in terms of the actual absolute minimum, there is only one, and that is -1. Then, if you were to ask yourself, does this thing have any relative extreme values? The answer to that one is no. At every other point on this graph, other than the 5 that I just drew in red, at any other point right here, let's just focus on this green point, what happens if you move left? The function goes up. And if you move right, the function goes down. And when it goes in different directions, vertical directions, depending on which horizontal direction you go, then you don't have an extreme value at all. That's not really a special point, despite what its mother might tell it. All right? That point is not an extreme value at all, and that happens really everywhere else you look on this graph. Here, or here, or here, any of these green dots, when you move left, the function goes up or down. When you move right, it goes the opposite direction. So this graph here has no relative extreme values, but it does have one absolute max and one absolute min. All right, let's keep going here, guys. Let me pull that up and let's take a look. Oh, this is a fun one here as well, just to test how well you can read a definition and apply that. Y equals 3, obviously, is a constant function. So a lot of people are going to look at this, and going back to my silly mountain example, they're going to think that this is like Nebraska. It's just one big flat expanse, and it has no peaks like Mount Everest and no valleys like Death Valley or that Mariana Trench in the ocean or something like that. I don't know what. You guys know that better than I do. So a lot of people want to say this one does not have an absolute max or an absolute min. And I get it, but you've got to go back and you've got to read that definition again. An absolute maximum is one y value that is greater than or equal to every other y value in the entire function. And in that way of looking at things, this one absolutely, haha, that's a pun, has an absolute maximum. The y value of this function that is higher than or equal to, that's what's important, every other y value is 3. This function is never going to reach a y value greater than 3, therefore 3 is your absolute max. And if that confuses you a little bit, I think this is probably why. Guess what its absolute minimum is? The one y value that is the lowest y value this function will ever reach, yep, that's 3 also. So this is a really silly example. You will never see a problem like this, I don't think, on a homework assignment or a quiz or a test. But just as a way of kind of like a mental stretch right here, a constant function, okay, has an absolute maximum and an absolute minimum, and they are both equal to that constant value in question. All right, let's move it right along, guys. Let's take a look at number 4. Let me slide this guy down. Oh, I had 3 more here. I lied. All right, what's going on in this one? So you'll notice I've drawn part of a nonlinear function with a limited domain. And what's significant here, everybody, is that we've gone ahead here and I've put a closed dot on the left endpoint and an open dot on the right endpoint. So let's start talking about what's going on right here. Do we have an absolute max or an absolute min? Well, I think we can tell right here. We do, everybody, have an absolute minimum. The one y value that this function reaches that is lower than or equal to every other y value in the range of this function is going to be 0. So that absolute minimum is going to occur at what I'm going to call point A right over here. Now, when I ask you guys for an absolute maximum, obviously everybody's going to look for the Mount Everest right here, and I'm going to call that point B. And they're going to say, okay, that y value at that point right there has to be your absolute maximum. Well, that would be true if point B was actually on the graph of this function. But the significance of the open dot, and this sometimes worries me, everybody, that it sometimes worries me that at this point we still don't understand the significance. The difference between an open dot and a closed dot is that point B doesn't actually exist on this graph. It's like a placeholder. All right. And so it would be wrong. Don't write this down, guys. It would be wrong here to say that your absolute maximum is equal to 5. In fact, let me change that right now. It's not equal to 5 because 5 is not in the range of this function. We've got that open dot there, which indicates that the y value here never quite gets to 5. Okay, well, if it can't be 5, it's got to be something a little bit less than 5. And that actually opens the door to a really interesting discussion that even smart people like yourselves in AP Calculus sometimes need a little bit of a bump in the right direction. Okay, let's think about this like middle schoolers. Middle schoolers would look at this and tell me that the absolute maximum is 4. Maybe. They might say that because they're going to reason, okay, if 5 doesn't occur, 4 must be the last number that does. See, middle schoolers and elementary kids, they think in terms of their fingers. Their number sense is almost entirely based on integers, so that they can only think about whole numbers and to say that if 5 is too big, then 4 must be the last number that works. You guys, though, are a little bit smarter than that. You know that a y value of 4, which might occur, I don't know, maybe right about there at a y value of 4, okay, that value exists. It is in the range, but you guys know that's not the highest y value that's here. You know that there are numbers in between 4 and 5 that work here. So now the really interesting question is this. What is the biggest number that's less than 5? So let's think about that. Is it 4.9? Well, 4.9 exists in the range of this function, and it is less than 5, but no, that's not the biggest number either, because there are an infinite number of numbers between 4.9 and 5. So how about 4.99? That's really close. But that's not it either, because again, there's an infinite number of numbers between 4.99 and 5. So how about 4.999? Nope, that's not it either. How about 4.9999? Nope, because I could just keep adding 9s here if I had the space to do it over and over and over again, and I can always come up with another number that's bigger than the one you gave me, but is still less than 5. And now, oh my gosh, I didn't want to spend too much time talking about this, but some of you guys are going to tell me that the absolute maximum then, I get the pattern here, Mr. Fontana, is 4.9 repeating. And that's not the answer either. Because now, I'm always surprised you guys maybe haven't had this conversation by the time you get to me. Now I'm really going to blow your mind. 4.9 repeating, you guys, is exactly the same number as 5. Whoa, I better explain that. All right, so this is a little bit of an aside. If you want to skip this part in the video, go right ahead. But here is what Mr. Fontana, a seemingly intelligent math teacher, just wrote down. 4.9 is equal to 5. Clearly, he has lost his marbles. Well, let me try to explain to you guys where this comes from. What we're going to do here, I'll go ahead and do this one directly. You could do it a couple of different ways, is I'm going to let x equal 4.9 repeating. So I'm going to go 999 and then just do a ... at the end of that. All right. The next thing I'm going to do, and I hope you guys are okay with this, I'm going to follow the rules of algebra, which I hope you guys believe, and I'm going to do something here. I'm going to take both sides of this equation that I just wrote down in blue, and I'm going to multiply them both by 10. All right. On the left, the x times 10 is going to give me 10x. I'm going to write that up above it here, 10x. And on the right side, I'm going to multiply the 4.999 times 10 and get 49.999, and that one goes on forever as well. Now, with what I'm about to do, this might be a spot that you guys have a little bit of a hard time accepting, but I'm going to tell you something here. If you take two true equations, and if they're in the same format, and add them together, you'll get another true equation. Let me show you what I mean. If we were in class, I would ask you guys for an example here, but let me just make up a couple of statements here. 7 plus 3 equals 10. Hopefully everybody's okay with that. Underneath that, I'm going to go with a 6 plus an 8 is equal to 14. Hopefully everybody's okay with that. And what I'm going to now do is take those two true equations and add them together vertically. The 7 plus the 6 gives me 13. The 3 and the 8 combine to make 11. And the 10 and the 14 combine to make 24. And wouldn't you know it, 13 plus 11 is equal to 24. Now, you guys actually know that this works because this was a basic idea behind what you guys did a lot of in Algebra 2 and a little bit in Algebra 1 when you were solving systems of equations by adding two true equations together and eliminating one of your variables. So you might remember doing something like 7x plus 2y is equal to 11, and then like an x minus 2y is equal to a negative 5. And if you did that, you'd add these together and get 8x. Those terms would cancel, would equal 6, and then you would divide by 8. That wasn't very nice, Mr. Fontana. And you'd get x is equal to 3/4, and then you'd plug that back in here and you'd solve for y. So you've done stuff like this before. It's just kind of been a while, and you don't do it much with constants, but it works. So what we can do is we can add two true equations and get another true equation, or, oh man, let me blow your mind even more, we can subtract two true equations and get another true equation. Let me show you what I mean. If I put a minus here now, and I probably should put brackets around all that, 7 minus 6 is 1, 3 minus 8 is minus 5, 10 minus 14 is negative 4. Yep. There's another true statement. So hopefully I proved my point. We're now going to subtract this equation from the one up above it. Let's see where that gets us, everybody. All right, 10x minus 1x is going to give us 9x. Now, I don't know how much you've done this in your life, but over here on the right-hand side, we are subtracting repeating decimals, which seems like a futile venture because those decimals go on forever. But as I think you guys can see, every time we go to subtract, it's a 9 on the top and a 9 on the bottom. And that happens with the 3 9s that I can see. It's also going to happen with every 9 over here that I can't see. So I'm left now with 49 minus 4, which is 45. So if this equation was true, which it is based on the fact that this equation is true, then this equation has to be true as well. So we're going to divide both sides by 9 and get x equals 5. Now look at the original statement we began with, guys. X was equal to 4.9 repeating, and we manipulated that and got x equals 5. Well, x can't equal two different things, everybody, without those two things being equal to each other. All right? So in Latin, everybody, we say QED, quotum eros demonstratum, oh, but I don't know what it stands for. I really should. It means thus it is proven, everybody. 4.9 repeating is actually equal to 5. That'll blow people's minds a little bit, but we don't need to spend too much time talking about that. Okay, so on to this one right here, everybody. Let's see what we have going on. So the point I was trying to make 10 minutes ago is that this one right here actually has no absolute maximum because, ladies and gentlemen, there is no largest number that is less than 5. Okay, so that being said, let me just do this a little bit better now. We can now say that this function right here, come on, has no absolute maximum. And that's what happens, guys, when you have an open circle on one of the ends here. No relative max, no relative min, because this function doesn't have any behavioral changes. Okay, so that's all we can do with D. Let's talk about E here and see what's going on. And again, I didn't set this problem up real well, but probably should have put some dots right here. I want to talk about this one right here, this one right here, this guy right here. I'm not sure why I put that blue dot right there, but we can talk about that, sure. And then this one, and then this one. So I see 1, 2, 3, 4, 5 points of interest that I've just marked in red, plus this rando blue one that's just kind of sitting in the middle. So let's talk about what's going on with each one. And again, I like to think about it in terms of the extreme values. Do we have an absolute maximum? 1 point higher than or equal to everyone else on the whole graph? Yeah, this one right here, guys, is our absolute max. Do we have an absolute minimum? 1 point lower than every other point. Yep, this one down here is going to be our absolute minimum. That's the lowest it's ever going to get. Now that's it for absolute max and absolute min. A function can only have one absolute maximum value and one absolute minimum value. However, we haven't talked about this yet, it can have multiple relative max or relative mins. I talked about Mount McKinley being the highest mountain anywhere around it. Well, that happens all over the world. Pikes Peak, I believe, is the highest mountain in Colorado. I don't know many other mountains, but I'm sure there's one that's the highest in South America, probably down in the Andes. There's probably one point that's the highest in Europe, up in the Alps. There might be another one that's the highest point in Russia or the highest point in Australia. So there are lots of relative maxes and lots of relative mins. So this first point, all the way over here on the left, guys, this one right here, ask yourself, is that the highest or lowest point in the neighborhood directly around it? It's the highest point, so this one right here is a relative maximum. This point right over here is the lowest point in the neighborhood directly around it, so that is a relative minimum. And then this point over here, the right end point, is the highest point in its neighborhood, so that one is a relative max. And before I move on and talk about that random blue dot, I do want you guys to notice something. If you read this graph from left to right, look at your extreme values. It's maximum, minimum, maximum, minimum, maximum. They alternate. Okay, if a function is continuous, as you move from one direction, you're always going to go back and forth between a maximum and a minimum. It's really not possible to have two maxima directly in a row without a minimum in between. Doesn't really make any sense. And the one thing I said we'd come back and talk about was this particular point right over here, maximum or minimum, and the answer is neither. We had talked about this a little bit earlier today, because as you move left from that point, the function goes up. As you move right from that point, the function goes down. And if it moves in different vertical directions, as you move in different horizontal directions, you don't have a max or a min. Okay, so that was E, and I wanted to talk about F here, because for the first time now, I think, I've drawn you a function that's not continuous. This one just has this big ugly gap right in the middle. But do notice the arrows going down in either lower direction there, meaning this one goes on forever. Okay, do we have an absolute maximum? 1 point higher than or equal to every other point on the graph? Yeah, we do, and that's this little peak right here. That's our absolute maximum. Oh, now I've done it. I don't even know what I hit right there. Not that, not that. This one. Whew, there we go. Next question. Do we have an absolute minimum? 1 point lower or equal to every other point on the graph? Answer to that is no. This one, because the arrows extend downward here and here, this one does not have an absolute minimum. It's always going to keep going downwards towards a y value of negative infinity. So the other thing to think about is what's going on at this point right over here. Well, what I can see is as we move to the left of that point, the y values go down, and there are no y values immediately to the right of that point. So therefore, this point right here meets the definition here of a relative maximum. It's higher than any of the points immediately around it. And those are the only 2 points of interest, or the only 2 critical points on this entire graph. This one does not have an absolute minimum, nor does it have a relative minimum. And then one thing that I do want to point out, this might seem to contradict what I said directly above it on example E. I said on E that as you move from left to right, your extreme values alternate, max, min, max, and that'll always happen. And that, oh, I just realized I moved that X here. That was weird. You, come on down. What's happening? Well, that was very strange. Maybe I moved everything else instead. Anyway, sorry about that, guys. This one, as you read it from left to right, has a relative max, then another relative max. Now, the reason that happens, when I said that wouldn't happen when we talked about E, the big difference here, and I'm hoping you guys can see it, is continuity. What I had described earlier in E, that the extreme values have to alternate between maxima and minima, that's going to be true so long as the function is continuous. But F has this big unnatural gap, this big jump in the middle of the function, and so that's what allows us to have 2 maxima next to each other without a minimum in between. All right, guys, I certainly have more that we need to talk about here within this section, but we got a class starting here pretty soon. So I'm going to wrap this video up for now, and I'll come back later today and I'll finish the rest of this up, and we'll post it in 2 different videos. Thanks, everybody.